Hello again, and welcome to another episode of Programming Problems. Sit tight, as today's a bit of a tricky one as we try to measure the capacity of our Lavaduct lagoon. To store all the lava, the elves have dug a large lagoon. However, they aren't sure the lagoon will be big enough, and so we are asked to come to the rescue by looking at their dig plan. The plan tells us how many meters to dig in a given direction, and what colors the walls of that section should be. An excerpt of today's input looks as shown below. Given a list of these digging instructions, how many cubic meters of lava will fit in the lagoon? Here is a full visual example, where we start in the top left corner and then we move 6 meters to the right. Next, we go 5 meters down, 2 meters left, 2 more meters down, and so on. The list of instructions traces the shape which you can see on the right. If we then carve away all the space that on the inside of the walls that were dug, then we can count the total capacity. Every position represents 1 cubic meter, so the total capacity is 62 cubic meters. Now, how to solve this efficiently? Let's take a look at a possible solution for part 1. Perhaps the most tricky aspect is that it is not clear where our digging starts, so we cannot immediately start drawing the walls on a grid. However, we can make a very large grid that will fit our lavaduct for sure, and then we just start digging from somewhere around the center. Computing the area on the inside then is as straightforward as doing a flood fill on the outside. Since this area, or volume in this problem, is simply the total area of our large grid minus the number of cells on the outside. The solution outline then looks as follows. First, we parse our input and we extract all the border positions from this. Then I went for an arbitrary size of 1,000 units, and I initialize an empty grid. On this grid, I draw the border, and finally we compute the outside using the count outside of border function. We'll skip parsing the inputs, but suffice to say that we get the list of directions and the number of steps along in each respective direction. Getting the border then is simply taking that plan, starting at 0, 0, and adding positions based on the direction and the number of steps in our plan. The border then is simply the set of all positions which we've encountered. Drawing the border then reduces to taking in our grid and the border cells which we've just computed, and the size of the grid itself. For every position in the border, we can add half of the grid size to offset it, and then we start filling in hash symbols. At the end, we of course return the grid itself. The last critical step then is to flood fill the outside to the number of cells. Here we can just start at 0, 0 again, and we do a breadth first search, as we've already done on multiple other days in this year's advent of code. A critical aspect here is that we, of course, need to check if any cell is not already visited, whether it is even in the grid, and if the cell is not part of the border. Note that because our grid is modeled as a dictionary instead of a 2D vector, checking if a position is in the grid has become trivial. We just see if the position is a key of the dictionary. And that was it for part 1 again. Let's see how much harder part 2 is today. For part 2, the elves realized that indeed the planned lagoon would be way too small, because someone swapped the color and instruction parameters from the dig plan. It is up to us to extract the correct instructions. After converting the hexadecimal color codes into the correct digging plan, how many cubic meters of lava would fit into the lagoon? For the examples, we'll focus on the hexadecimal conversion. What we're asked to do is to split the color code into 2 parts. The first 5 digits are a number in hexadecimal, or base 16. The last digit is always 0, 1, 2, or 3. And represents the 4 directions as shown. So the example on the slide translates to dig 1 meter to the right. Here are some additional examples which are provided to us at adventofcode.com. Make sure to check your implementation against them. Note how much larger these values are. That's going to be a challenge. Let's move on to the solution. Flood filling will be way too slow as the lagoon has become very large. However, the pool border forms a simple polygon, and computing the area of a simple polygon is a well-known problem. We can compute the area using the shoelace algorithm. The gist of the algorithm is as follows. Given a series of points as x and y coordinates as shown on the right, we can multiply inside each respective colored bar. So for the blue bars, we can do 1 times 3 plus 1 times 7, and so on. And then we can do the same for the green bars. Finally, we subtract one from the other, and this is twice the area of the polygon. Note that this value is potentially negative, so we just take the absolute value to compute our answer. Visually, it works as somewhat like follows. Suppose we have this simple polygon with 3 points. Then from the origin on the bottom left, we can simply compute the green triangle. Then we add the area of the next triangle using the next 2 points. Finally, we take the last 2 points, and we subtract the area as it is wrapping back around. The result is the green area that is exactly the area of the triangle. The shoelace algorithm helps us compute this in a very simple way. However, before we look at the code, there is a significant remaining challenge. We dig 1 meter cubes, but where is the edge of the polygon located? Actually, the edge runs across the center of the border. So we must be careful to not double count the overlap here. We can solve this by offsetting our edge to match up to the outline of the border, but I think the following solution is more interesting. Given this rectangle, we can actually distinguish between edges and corners on our border. All edges, colored blue here, simply need to be divided by 2 to determine the overlap with the green center area. For the 4 green corners, do you see how every corner overlaps with 1/4? So in this case, you can see that the non-overlapping border area is simply the number of border cells minus the 4 corners, divided by 2, and then we just add 3 corners worth of area back. However, does this generalize? The border is not a simple rectangle, but I claim that for today's Part 2 problem it actually does generalize. Let's visualize the area again, and then let's also draw the corners. For visual clarity, I separated the outer corners from the corners on the inside of the shape. Do you see how there are now way more than 4 corners? Because this problem is on a 2D grid, we can make the observation that to close the loop, we'll always have to turn the corner exactly 4 times. At its smallest, this is just a 4-block square. In larger examples, it means that turning 1 additional time to the left or the right requires us to also undo that turn by turning the opposite direction at some later point in the path. Hence, here you can see pairs which basically cancel each other out. Do you see how every pair has, in total, 1 full cell worth of overlap with the green center area? The result is that the same formula holds for complex polygons like our input. The high-level outline then is the following. We update the way we parse our input, and then we compute the border area based on the plan. Then we compute the inner area using the shoelace algorithm, and finally, we correct the border area for the overlap. Parsing the hex codes can be done as follows. Note that now we return just a list of 2D vectors instead of the direction and distance count. We do this because it no longer makes sense to step over that distance to actually construct the border like we did in Part 1. Computing the total border area is simply summing those vectors which we got from processing the input plan. The shoelace algorithm requires us to get the coordinates of the corners of our polygon. We can determine these from the plan itself, but assuming that we have them, then applying the shoelace algorithm is as simple as follows. You extract all x and y positions, and then we can loop over them in pairs while multiplying them out and adding them to the result. This is equivalent to the blue laces on the image. On the second loop over the pairs, we subtract the result, which matches with the green laces on the image. In the end, we take the absolute value and we divide by 2 to get the actual area. For completeness' sake, here's how to move from the plan, which is a list of offsets or directions, to the actual list of corners. We just start at some position, in this case 0, 0, and we set that as our first corner. Then we keep adding each offset in our plan to the position, and we append to the list. Then last but certainly not least, we of course have to correct for the overlap on the border area as explained earlier in this video. And now you too should be able to obtain the 2 stars of today's problem. Thank you for sticking with me on what has perhaps been quite a tricky problem. Don't forget to like and subscribe, and let's look forward to next day's problem.